Hi, everyone. Today we are starting the last lesson in Chapter 5. It is another area approximation method, actually two of them, one called the trapezoidal rule and one called Simpson's rule. Tomorrow you work on homework from these two things, and then we'll start reviewing for the test. Okay, so the first method we're learning is called the trapezoidal method. So to help kind of understand where this is coming from, I'm going to remind you of the area of a trapezoid so that you could actually go back and use this formula if you had to, if you forgot the trapezoidal rules separate formula. So the area of one trapezoid is 1/2 times the height of the trapezoid times base 1 plus base 2. Or probably we will write it like this: h divided by 2 times base 1 plus base 2. So just like our methods from before, when we were doing rectangular approximation methods, we were creating rectangles. So now we are going to be creating trapezoids. So let me show you an example of it. So here's a picture of just some random function here. So it's a red function here. And we drew in these little trapezoids. So they're drawn by connecting, this would be your left bound, this would be your right bound, and connecting all of the heights at each of your little subinterval distances. So this would be your first base would be this length of this vertical line, and your second base would be the length of this vertical line. And then the height would be the distance between the two verticals. So base is here, another base is here, and the height is the distance between the two. Okay, so we're going to write a formula that will relate to that. So looking at this graph, you can see that it's written in general form. So the distance between each of these little things here is what we would call the height, okay? So the area of the first trapezoid would be the height divided by 2 times base 1 plus base 2. Well, base 1 is the y value from the function because it's the height of this first side here, so it would be y naught. And then the second base would be y1, the next y value. And then I would go on to the next trapezoid, sorry. So the next trapezoid would be h over 2, same height, times, well, now my next y value is y1, and then y2. And I could keep going, as many rectangles as I have. My last rectangle, excuse me, would still have a height of h right here. Its like base 1 would be y sub n minus 1, and the last base is yn. Well, it's really a messy formula, so we're going to try and simplify it a little bit. So the simplified version would come from factoring out an h over 2, and then noticing there's only one y naught base. But for every trapezoid in the middle, there will be 2 of each of the other bases. So do you see how there's a y1 here and a y1 here? So there's 2 of them, 2 y1s. And then there'd be 2 y2s. And there would be 2 yn minus 1s. But all the way at the end, on the right side, there's only one base that's a yn. So your formula, simplified formula, get this stuff out of the way, looks like that. Y naught plus 2y1. So basically, without me reading it all over again, you've got the first base is multiplied by 1, everything in the middle is multiplied by 2, and the last base is multiplied by 1, all multiplied by the height divided by 2. This formula is actually equivalent to LRAM plus RRAM divided by 2. So you could do that if you have those, if you know how to do this, but you have to do both of those in order to make that work. This is a really useful method when you have a table of values, as we'll see in a minute. All right, so we're going to do our first example, and I'm going to try and do a decent job graphing this with the pen. So my first example is from 0 to 4 with 4 subintervals. I want to use the trapezoidal rule. So I have 1, 1, 0, 0, I forgot, 2, 4, 3, 9, and then 4, 16 way up here. So let's see how good of a graph I can do. I bet you not so hot. When I'm done, just please humor me and pretend it looks great. Okay, so in order to use the trapezoidal rule, what you're doing is you are drawing up these little vertical lines from your subinterval's starting point up to the function. And then you're connecting each of those little heights with another line, kind of, again, making just a trapezoid out of it. In this particular problem, though, the first trapezoid is actually a triangle, but it will not matter to the problem at all. So I've got a triangle here and then 3 trapezoids, but it won't matter at all. Okay, so my first thing I want to do is figure out the height of each one, which we already said was 1. So then it's going to be 1 divided by 2, or 1 times a half. My left value comes from substituting 0 in. So 0 squared plus, then all my stuff in the middle gets multiplied by 2. 2 times 1 squared, because 1's the next value, plus 2 times 2 squared, plus 2 times 3 squared, and then 4 is my last value, so that one gets multiplied by 1, or just left alone. So it looks like now I have 2 plus 8 plus 18 plus 16. And if I add those all up, I get 44 divided by 2 is 22, the approximate area under the curve. So this says, since we could have found the exact answer for this integral, meaning we've done enough of this stuff now, you know how to do this. This is 1/3 x cubed, and we evaluate that from 0 to 4. We know how to do that by, an exact method by now. But the trapezoidal method is very beneficial when you don't have a function. So we'll do one of those in just a second. Okay, so now we're going to practice a sign problem. So just something with trig. So let me get an actual line here. So I'm going to quickly draw a sketch of this as well. So I'm going from 0 to pi. And 2 sine squared x probably looks something like this, I'm going to guess. Kind of. Okay, it's an approximation. If I'm doing 4 subintervals, that means the height of each of them will be pi over 4. And I am dividing pi over 4 by 2, or multiplying pi over 4 by a half. So h over 2 is pi over 8. And then I'm going to sub each of my values into the function and simplify. If you want, you can take this 2, since my function is 2 sine squared of x. You could take this 2 and factor it out front. It might make it easier to do the problem in the long run. So I think I'm going to do that. I'm going to put the 2 out here. So now I'm just working with sine squared x. So I'm going to do sine squared of 0 plus 2 sine squared pi over 4 plus 2 sine squared pi over 2. Of course, I'm going to run out of room. Plus 2 sine squared 3 pi over 4 plus sine squared of pi. My stuff out front is now pi over 4. Sine squared of 0 is 0. My next term is a 1. I'll let you guys see if you can figure out why. If you're not sure, just substitute it in your calculator if you need to. This is a 2. This is a 1. And the last term is a 0. Add it all up, multiply by pi over 4, and you end up with pi, a pretty nice answer, when you are done. Okay, so now we're going to try a problem that's just data and not an actual function. So this is just random data that I made up here. So I'm going to plot these points so you can kind of see what's going on and visualize the trapezoids. You don't have to do that, but sometimes it's helpful. So I have the first point is at 0, 8. Then I'm at 2, 11. 4, 10 goes back down. 6 all the way up to 14. 8 to 13. And I would want to help me probably to draw some vertical lines so that I can see the bases. So there's a base, this is a base, this is a base, and this is a base. And then I'm going to connect to visualize my trapezoids. So the height of each of the trapezoids is 2. My y naught base is 8, and the very last base that I have is at 13. All right, so to do this one with the formula, remember you take the height, which is 2, and divide by 2. And then the first base, which is 8, does not get multiplied by 2. My next 3 bases would, so this is an 8, this is 11, 10, 14, and 13. So this becomes 8 plus 2 times 11, plus 2 times 10, plus 2 times 14, and then plus 13. Add it all up, and you end up with an area that approximates whatever this curve was. Maybe it's something like this. Who knows? We have no idea. Whatever this curve was, approximating the area under this curve would be 91. You'll see this method, the trapezoidal rule method, used a lot with data because it does come pretty close to getting an accurate answer. All right, last thing is we're going to learn this last method that's called Simpson's rule. So I didn't even want to show you the graph of it because it's really hard to get decimals to look nice with it. But Simpson's rule is another way to approximate the area under a curve. And what it does is it approximates it using parabolas. So if you can kind of visualize as best you can with this picture that I have over here. So this was like whatever these values were with some function, and this would be like a part of a parabola here, and this would be a part of a parabola here, and part of a parabola here. So we're creating like little mini parabolas that we're finding the area underneath. The formula requires that you have an even number of subintervals, so you can't use it with an odd number. And it looks kind of similar to the trapezoidal rule, where you don't multiply your first y value by anything, but then the second one by 4, the third one by 2, the fourth one by 4. So notice it rotates between 4, 2, 4, 2, blah, 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 so that the last one has nothing it's multiplied by, and the one before it's multiplied by 4. So it's like a symmetric thing through the middle. The height is actually found by taking the bounds and subtracting them and dividing them by the number of subintervals. So that's actually where the height comes from. And then you take the height and divide it by 3. All right, so for this problem here, we already did this one with the trapezoids, so now we're going to do a Simpson so you can see kind of compare them. So the height will be pi minus 0 divided by, we want 4 subintervals, so divided by 4. So my height will be pi divided by 4. We already did this. But then we're going to divide that by 3 for the formula. So pi divided by 4 divided by 3 is pi divided by 12. Then the formula is going to have a substitute 0 in first. So it's just like the problem we did before with the graph of that sine squared graph. I'm going to leave the 2 in the problem for us this time instead of factoring it out. So 2 sine squared of 0. Now the next thing should be a 4 times, you know what? Let's take that back. I think this 2 in here is going to make it really confusing. So I'm sorry, as I started to write it, I felt like I didn't like where that 2 is at. So I'm going to take that 2 and put it out front here. All right. So now when I'm multiplying, I'm just using the sine squared. So it's going to be sine squared of 0, oops, plus 4 times sine squared of pi over 4. Plus 2 sine squared of pi over 2, plus 4 sine squared of 3 pi over 4, plus sine, no number that's multiplied by this time, sine squared of pi. I'm going to let you calculate all of this out if you want to. But strangely enough, using Simpson's rule, you get the same answer. It turns out to be pi. All right, I hope that you're understanding this. Remember to write down any questions that you might have so they can be answered in class tomorrow. See you then.